A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about the Kronecker Delta operator and its application in the vector dot products. So let's get started. So let us start with the first vector operation, that is vector addition. So we'll write this in the symbolic notation because we are used to that till now. So the vector W is the sum of the vectors V and U in the symbolic notation. So if I expand this, we get this expression. So as we know that the basis vectors E1, E2 and E3 are orthonormal, so they're orthogonal, that is they're independent. So what that means is that the components of E1 on both sides have to be equal, and same is the case for the components of E2 and E3. So we get W1 is equal to V1 plus U1. Similarly, W2 and W3 are V2 plus U2 and V3 plus U3 respectively. So this gives us the general expression in the initial notation for vector addition, which is Wi is equal to Vi plus Ui. So this I'll say is the initial notation representation. So in this expression, I is a free index. And this expression is general in I, in the sense that I can take any value. So this expression is true for I equal to 1, 2 and 3, all values. So this is the way we write vector addition in the initial notation. So in this course, we'll be using this way for writing that, W is equal to vectors V plus vectors U. So let's move on to the next vector operation, that is scalar multiplication. So scalar multiplication simply is that the vector V can be written as some scalar alpha times the vector U in the symbolic notation. Now if I write this in the initial notation, this simply becomes Vi is equal to alpha Ui. And this is true for all values of I. So remember, I is a this expression is general in I, in the sense that I can take any values from 1 to 3. So this is true for all values of I. So next we'll move on to vector multiplication. And in vector multiplication, we will start with the famous vector dot product. So before we actually start discussing the vector dot product, we first need to understand an important symbol, that is Kronecker delta. So we will park ourselves here, and from this point onwards we'll talk about the Kronecker delta symbol, and then we'll come back to the vector dot product. So let's discuss this in a fresh page. So the Kronecker delta symbol is written as the Greek lowercase alphabet delta with subscripts I and j, and this is defined as follows. So delta ij is equal to 1 if the indices I and j are equal, and this is equal to 0 if the indices I and j are not equal. So remember, this is a definition. So it's a very important and a very useful symbol, and the motivation behind delta ij, as you may already have guessed by now, is the vector dot product. So let's see how this helps us in the vector dot product. So if I write ei dot ej, where e is a unit vector, so ei is a unit vector in the I direction. So this is equal to, and this is by not by definition but by the nature of the unit vectors. So if I is equal to j, then this becomes if the value of I is equal to value of j, that is if I and j are both equal to 1, so this is e1 dot e1, so this becomes equal to 1. So if I equal to j by values, then this is equal to 1. But if I and j are not equal by value, then it's equal to 0. Okay, and we can easily see this because they are orthonormal. So we can see that e1 dot e1, e2 dot e2, and e3 dot e3 are all 1, and any other combination, they're all zeros. So we can see that ei dot ej actually is equal to the Kronecker delta delta ij. So this is where the Kronecker delta symbol helps us use it in the vector dot product. So we'll use that later, but before that there's an important property of the Kronecker delta that's called the substitution property of delta ij, and that is something we'll discuss now. So let us try to understand this property. So it says if delta ij is multiplied with another tensorial quantity and one of the indices of delta is repeated. So let's underline this. So one of the indices of delta is repeated, then we can simplify the expression by getting rid of the delta and replacing the repeated index. So replacing the repeated index by the other index of delta. So let's understand this through examples. So we have an expression delta ij uj, and we want to use the substitution property here to simplify this expression. So let's read the property again. So if delta ij is multiplied with another tensorial quantity, so that is true. So delta ij is multiplied to another tensorial quantity, which is a first order tensor uj, and one of the indices of delta is repeated. So delta has two indices, I and j, and we can see that the index j is repeated. So that condition is true as well. Then we can simplify the expression by getting rid of the delta. So the simplified expression will not have any delta, it will only have a u, and replacing the repeated index by the other index of delta. So the repeated index here is j. So let's write that down. So we'll replace this by the other index, which is j, which is I, right? So this is the simplified expression that we have here. And remember that in the simplified expression, you cannot have a j as a free index, because j is a dummy or a repeated index. So if we were to simplify this, then j will be gone, right? In fact, let's expand it. It's not very difficult to understand this property by expansion. So let's do that and get a feeling of it. So if I look at, let's expand the left hand side. So you have delta ij uj, and this is basically j going from 1 to 3. This is from the Einstein notation or the summation convention. So which expands to delta I1 U1 plus delta I2 U2 plus delta I3 U3. Now we can see that in each mathematical term, there is only one free index I. So I can take any value. So let's say the I value was equal to 1. So let's take case 1, that I is equal to 1. So in that case, the expression becomes delta 11 U1 plus delta 12 U2. Now delta 11 is a 1, but delta 12 and delta 13, they are both zeros. So what we are left with is simply U1. Similarly, if I was equal to 2, then the expression would have been U2. So we can see the pattern here, that in the final expression, will ultimately become ui, which is equal to the right hand side. So let's look at one more example. So in this example, we have delta ij ui vk. So in this case, the index I of the delta is a repeated index. So from the substitution property, we can simplify this expression by getting rid of the delta. So we only have u and v now, and replacing the repeated index of delta with the other index. So the repeated index in the delta with the other one. So I was a repeated index, So in the simplified expression, we'll have I replaced by the other index of delta, which is j. So the final simplified expression is ujvk. Alright, so now that we understand this Kronecker delta symbol and its substitution property, let us go back to our vector dot product. So if I was to use the symbolic notation, then I would have written u dot v and I would have expanded this. So this would have become u1 e1 plus u2 e2 plus u3 e3 dotted with v1 e1 plus v2 e2 plus v3 e3. And when I expand this, I get u1 e1 dotted with a v1 e1. So that basically becomes u1 v1 times e1 dot e1, which is a 1. Then I take this u1 e1 dotted with a v2 e2, that becomes u1 v2 times e1 dot e2, which is a 0. So what we can see is basically we'll end up with u1 v1 plus u2 v2 plus u3 v3. All the terms where we have an e1 dot e1 and an e2 dot e2 and an e3 dot e3. So this is something we already know. We have been doing that for a long time. But let's do it using the indicial notation. That is what is important today. So if we use the indicial notation, so remember we are starting with vectors u dot v. That's the expression we want to solve for. So u can be written as ui ei. Remember, we are using the summation convention, so I don't need to put a sum symbol here. And v vector can be written as vj ej. Again, this is exactly the same as what we had above, where I had written this expression, because it ultimately expands to this above expression. Right? So this is where the beauty of the indicial notation with all its rules such as summation convention, they can be seen. So you can see that we don't have the sum symbols here, but we will still open these brackets. So you can see that ui and vj, they are simply scalar components of vectors. So they can be separated out. So this becomes ui vj, and then we have the term ei dot ej. Put this in brackets. So there's no sum symbol, but still we are comfortably doing the algebra. And now we already know that ei dot ej is the Kronecker delta symbol. So this becomes delta ij. And we can also see that one of the indices of delta is repeated. In fact, both of them are in this case, but for our application, let's assume that I is the repeated index of delta. So then what we get is, if one of the indices of delta in an expression that multiplies delta with some other tensor is repeated, we can get rid of the delta. So in the final expression, we'll only have u and v, and we replace the index I with the index j. So we get a uj vj, and you can easily see that this will expand to u1 v1 plus u2 v2 plus u3 v3. So this is getting the expression using the indicial notation. So the whole aim here was to let you do an algebra on the indicial notation. So here we applied the indicial notation, the summation convention, and the substitution property of delta all in one go. Right, so before we close this lecture, I'll want to give you one more example in the indicial notation, particularly with the use of delta. So the problem says simplify the expression delta II. Okay, so this is independent of the vector dot product. We are done with that. So how do we proceed? Now we can see it's an indicial notation. It involves a delta. So the first thing we have to do is to apply the summation convention, because as per the convention this has to expand to something, right? So we apply the summation convention. So this is actually equal to sum I going from 1 to 3 delta II, which expands to delta 1 1 plus delta 2 2 plus delta 3 3. And now we apply the definition of the Kronecker delta symbol, which says that delta 1 1 is equal to 1, delta 2 2 is equal to 1, and delta 3 3 is equal to 1. So this simplifies to a value of 3. So delta II is equal to 3. Now the reason I discussed this case is that many students do this mistake where they say that delta II is equal to 1. And the mistake they make is that they say that since the indices of delta are both equal, so by definition it is equal to 1. So the mistake here is that first you have to apply the summation convention and expand it, only then you apply the definition. So we will write this rule because this will confuse us at many stages. It may be clear at this stage, but when you have a complicated expression, we end up sometimes making this mistake. So the rule says always expand the summation first, then apply definition. So if you remember this rule, or you use this rule when you solve problems, practicing them, you will be comfortable with expanding complex expressions involving multiple symbols such as delta and others as well that we'll discuss in the next lectures, and the use of summation convention in the indicial notation. So this brings us to the end of this lecture. Today we discussed the Kronecker delta symbol and its substitution property. We did a couple of examples to reinforce our understanding, and we then applied that to the vector dot product to understand how to use the delta symbol and its property in with the use of indicial notation. So we did some algebra with the indicial notation today. By the way, this Kronecker delta symbol is also known as the substitution operator sometimes. Because of the reason that we almost always substitute the delta by removing it and replacing the index in the expression. So it's sometimes called the substitution operator. Right, so in the next lecture, we'll go beyond vector dot products. That is, we'll be studying tensor products in the coming lecture in the next week. Next, we'll have a tutorial this week where we will practice problems from the topics that we have done or discussed in this week. So before we close this lecture, let's do a quick concept check. So the first problem asks us that is delta ij the same as delta ji? So go to the definition of delta and see if you can answer this question. And the next question says that we have to simplify this expression, that is delta ij times sigma jk. So again, to simplify this expression, you look at the definition of the substitution rule or the substitution property and go step by step and try to simplify this expression by getting rid of the delta if you can. Thank you very much, and I'll see you in the next tutorial.